So we have quite a few interesting talks lined up, 6 in total, and we are going to start with the first one, DeepSE-WF, which will be given by Diogo, who is an assistant professor at University of Waterloo.
Okay, thank you for the introduction, Piyush. So it's really nice to be here today, and thank you for being here so early in the morning. So today I'm going to talk about website fingerprinting defenses and how we can better estimate their security. So this is joint work with Alex and Cedric, who unfortunately weren't able to be here today. So I'm also going to speak for the team. So something that most of you on this room probably know is that encrypted internet connections do leak some metadata, right? So in a typical setting, Alice might want to access some website, but she might be concerned that her ISP, or for instance, the manager of her cyber cafe, is actually trying to reconstruct her browsing behavior and her browsing history. So what Alice will do is to use some kind of encrypted tunnel to access a website, for instance, WebMD, because she might be worried about her health or something like that. And she will connect to either a VPN or Tor to browse securely, right? So what this means is that even if an adversary is eavesdropping on Alice's internet link, they won't really be able to know that Alice is accessing WebMD. They will just know that Alice is accessing some VPN nodes or that Alice is accessing some Tor relay, right? However, these eavesdropper can actually see a few more things than that. They can actually reconstruct the packet exchange that Alice is exchanging with the server, right? So some of the things that this adversary can observe is metadata, for instance, the volume of the communication, like the total number of bytes exchanged, and also the sequence of packets exchanged between Alice and the server, the size of these packets, the direction, the inter-packet timing, and so on. So this might not be like doesn't seem like a big thing, right? The adversary still doesn't know what website Alice is accessing directly. But these metadata is actually allowing an adversary to launch what we know as a website fingerprinting attack, right? And the idea here is that the adversary will try to use the same encrypted tunnel as Alice would, and then would also try to browse different websites and recollect the traces when they are accessing these websites. So for instance, the adversary could access WebMD, could access some other websites on the Swiss Medical Network and so on, and keep a signature or a fingerprint of how an access to that website looks like. So of course, this is not like a single fingerprint because we don't really have two exact same traces when accessing just a given website, but these should be reasonably similar such that an attacker could use, for instance, a machine learning classifier to, once they have an observation on the traffic of their targets, they can try to match it with one of these websites, right? So that's exactly what happens after the adversary builds this kind of database. They will observe Alice's connection and then use this classifier to match the website that Alice was accessing through the encrypted tunnel. So we as a community, we do know about this problem, and some of us have actually been building defenses against these kind of attacks, right? So for instance, an example defense could be randomized padding, where actually these, for instance, a Tor relays, specialized Tor relays will actually add some packets to this connection. For instance, they will add dummy packets, here shown in purple, with different sizes or different direction and different timing properties that will screw up this kind of signature such that the adversary cannot really build a database of these accurate fingerprints, then making its task more difficult. So the next question is, okay, so but now that we have these defenses, so how can we tell how good the defense is, right? So the typical thing that people will do to analyze the security of these defenses would start by coming up with an attack, right, for some traces. And we as defenders will build a new defense, right? And so we'll try to tweak it, and then we'll try to check the accuracy of the state-of-the-art attacks against the defense that we are building, right? So if the attack's accuracy is high, then it means that our defense is still not there yet. We might need to redesign it, we might need to tweak some parameters of this defense, but eventually we might actually be able to get something that once posing against this kind of attack actually allows us to get a low accuracy on that attack. So we kind of come up with a new defense, but then this is an arms race, right? And so our adversary will try to come up with a new attack and so on, perpetuating this cycle. So if we actually do this, then we can see that this kind of evaluation life cycle is very dependent on new attacks that people are devising or the classifiers that are tied to these kind of attacks. So previous research has actually moved towards this kind of idea about an attack-independent evaluation of defenses. And they try to estimate different quantities that can tell you how secure a defense may be, regardless of the classifier that's being applied there, okay? So one of such works has actually been proposed in a past PETS that was called a framework called WFS that tried to estimate the Bayes error rate. And so in kind of simple terms, these Bayes errors rate and this framework try to estimate the smallest error that any classifier could achieve given a predefined set of features. And the way that WFS computed this base error was by using the error of a one nearest neighbor classifier as kind of a proxy to estimate the lower bound of that error on any classifier. Another approach was WFDE, proposed 1 year later, that estimated a different quantity. They estimated information leakage. And the idea was to compute the mutual information between features and the labels of a given website, such that we could even, for instance, say how much a given feature contributes to an attacker being able to identify a website despite a defense. Now, one thing that is common to both of these approaches is that they use manual engineered features to compute these estimates of security. However, we actually see nowadays that attacks are no longer using these kind of features, these engineered features. So in this kind of cycle, you can see that you will typically depart from a raw representation of our traffic, like your Wireshark traces. We then convert them to packet sequences. And now one of two things can happen. We either extract manual features like summary statistics about these traces and use them to train a classifier, or we just feed these packet sequences into a deep learner and allow the deep learner to extract some latent features in an embedded feature space. Now, the disconnect here and the pitfall of these kind of security estimators is not that we are in this kind of setting where attacks use a certain kind of features, defenses might try to defend against another set of features, and the estimators are also using different sets of features, right? So what this actually means is that also these latent features have been shown to actually preserve more information than the manually crafted ones. And so now we have a disconnect because these security estimators are estimating security based on something that actually preserves less information about traces. So in this work, we propose DeepSE-WF, which is this new security estimation framework for website fingerprinting defenses, where we attempt to estimate the base error and the mutual information of website fingerprinting defenses using these latent feature spaces, and thus approximating the kind of features that current attacks are using to also evaluate our defenses. So we implement and evaluate DeepSE, and we compute a lot of experiments on Tor traffic. So kind of an overview of our framework is as follows. So we start by generating some defended traces on the Tor network. This can be achieved by either applying defense simulators or actually collecting live defended Tor traffic. And then we pick a bunch of different neural network architectures, typically drawn from common attacks like TikTok or deep fingerprinting, VAR-CNN, and so on. And we generate the learned latent features that each one of these attacks would create. And after this, we apply a KNN-based estimator that can actually give us an estimate of the base error or these mutual information. And we take the minimum estimate that we can get for the BER across all these latent features for a given architecture, and we take the maximum one for mutual information. And we'll see why just in a couple of slides. So for estimating the base error, we use the 1NN estimator proposed by Cover and Hart in the 60s. And the idea here is that this estimator can, again, estimate the security of our tools by giving you the base error rate, so the minimum error that an adversary will be able to achieve. And we also rely on this new theoretical result, which is quite recent, that says that any kind of feature transformation, so once we go from a raw representation of the data towards some feature representation, these transformations can only increase the error, but not decrease it. So what this means is that we are safe to apply any kind of learned latent feature transformation and estimate the BER on it, and it's kind of still safe in some sense. So we do that, and now DeepSE can actually keep these theoretical guarantees proposed by the Cover and Hart estimator over any possible feature transformation. So that's why we need to train different latent features with different architectures, and then we just pick the one that gives you the minimum base error. For mutual information, this is quite similar, albeit in kind of a reversed way. But so we also use a KNN-based estimator proposed by Ross in 2014. I'm going to spare you with the mathematical details here. But the idea is that these transformations are also proved, as we do in the paper, to only decrease the mutual information, but not increase it. And so this also makes sense, because the defense will actually try to decrease the mutual information between the features and the labels. But we show that these transformations can actually only decrease that. So for the adversary, then, they will try to use the latent transformation of features that will get the maximum mutual information about all the one feature transformations that we tried out. So I'm just going to tease you with a few results. There are plenty more results in the paper. But so, for instance, we started to compare DeepSE with the first estimation framework called WFS. And so here we are using the subset of the AWF dataset, which is a well-known dataset for website fingerprinting. And so for 100 websites, we pick 90 traces, and this is the results that we get. So for instance, for the front T1 defense, which is this kind of randomized padding defense, what we can see here is that WFS provides an estimate on the base error rate, which is actually close to the actual error of the TikTok attack, but we can actually see that WFS is overestimating the error that the adversary would have. So in practice, what this means is that we actually come up with an attack that is more accurate than what WFS will say a potential attack can be, right? And in the other way around, our DeepSE estimator can actually estimate a base error which is smaller. So what this means is that there is potentially an attack that gets closer to that 0.5 error there. So then we also tried to use more data to perform these estimations. And what you saw is that these old security estimation frameworks are more demanding on resources. So for instance, WFS would exhaust the resources of our experimental test bed after these 90 traces were considered for each website. With DeepSE-WF, we actually saw that we could process all the traces that are existent in this AWF dataset, so all 4,500 of them. And we can actually see with more data that, of course, like this TikTok attack error gets decreased by benefiting of more data being available to just 16% of error. And in the DeepSE estimator, what we get a base error estimation of 10%, which means that even TikTok gets this kind of 16% of error. There might be still an attack using these features that might be even more accurate than that. So for other comparison, we compared also with these other estimation framework, FDE, that estimates mutual information. And one thing that we saw when we put together 500 traces of each website, which again was the maximum number of traces that we could analyze in our test bed for FDE, we saw that the joint mutual information that was being estimated seemed to be quite high for all the defenses, which we found weird, at least for this data set, because, for instance, for Tamarol, that is a very strong defense, WFDE would output a very high mutual information, saying that it seems that this defense is leaking a lot of actual interesting information to an attacker, when in fact we didn't think so, and at least our results are kind of more congruent with what we were expecting to see. So that a stronger defense would leak less information than other not so good defenses, so to speak. So again, there are more results in the paper, so I welcome you to also check our paper. But as a few takeaways from this presentation, I just wanted you to keep in mind that we know that previous security estimators are not able to provide these tight bounds on the security of the website fingerprinting defenses. So we use these latent feature spaces to try to come up with better security estimations that use the same features as current attacks do. And we also identified a few limitations in DeepSE, which in the interest of time, I'll be talking during the Q&A if you'd like me to elaborate on those. Thank you.
So thank you for the talk. We have one question online by Aaron. So could you estimate change if you change or improve the feature extractor?
Yes.
Another way, why does the estimate generalize beyond your model choice?
Right, so that's actually a great question, and this is actually one of the claims that we do not make in the paper. So DeepSE, as we can see here, is actually kind of not attack agnostic, in the sense that our estimate is only as good as these architecture that we use for deep learning to extract these latent features, right? And so that's why we need to test a lot of them. So these large number of transformation as I had here in this slide. So we go over different architectures, and then we either pick the one that gives the minimum base error or the maximum mutual information estimation. But that's right. So there's not kind of a general way that we could measure it without having access and just trying different architectures. However, we do know that according to these theoretical results, these transformations will never increase the base error or decrease mutual information. So we're kind of safe in that sense that we can try them, ideally all, although trying them all is probably something not feasible. Yeah.
So we do not have any other question. Maybe I can just ask one very quick general question. To what scale of websites do you think that your work can actually work for? Like, what is the scale of closed world websites for which you can do the evaluation realistically?
So that's a good question. So in our experiments, we actually just used 100 websites. We did increase the number of websites, the number of choices per website that we were using. We did not really try with more or less websites because, 100 has been kind of the golden number to evaluate many of these defenses. But that's actually a good question, and we can definitely try that in the future.
So, yeah, I think there is one more question, but maybe we'll have to leave that for the time, and you can respond on Tulip. So, thank you for the talk. And